Welcome to the third of 4 Physics 30 review videos. In this video we'll be looking at Unit C, electromagnetic radiation. What do pith balls and magnets have to do with each other? And what do they have to do with light? A lot more than you might expect actually. Click the pictures below to find out. If you're not happy to be Scottish after that, maybe haggis will do it for you instead. The various regions of the electromagnetic spectrum are named. If you're having trouble remembering their order, click the picture below. Or don't. You might never forget if you do. We looked at a few of the ways the speed of light was measured throughout history. Michelson's setup, shown here, was covered pretty heavily in this course. A photon is shot at a rotating 8-sided mirror and travels a far distance to a fixed mirror and back. If the mirror is rotating too slow, the photon doesn't quite make it into the collector at B, and we can't make a measurement. On the flip side, if the mirror is rotating too fast, the photon overshoots the collector. If the rotating mirror makes 1/8 of a rotation while the photon is traveling to and from the fixed mirror, we're now in a position where we can determine the speed of light. So we know that speed is distance over time. The distance we use here is twice the distance from the rotating to the fixed mirror. The other contributions are pretty small, and the time we use is 1/8 the period of the rotating mirror. The formulas we use for this unit are roughly categorized in terms of the property light is demonstrating at that particular moment. On the wave side of things, we've got a few Physics 20 formulas in here. Just ignore those. You might end up using this one, the relationship between frequency and period. You'll use this one, the wave equation, except we'll generally sub in the speed of light for V. Might as well call this the magnification equation. It relates image and object heights to image and object distances. We've got the lens equation, which relates the focal length to image and object distances. We've got the expanded version of Snell's law, which deals with refraction. We've got this equation for interference patterns. It's not always the most useful equation under experimental conditions, unless you're able to measure small angles. On the other hand, this formula is generally more helpful when you're doing interference experiments, and we don't have to measure small angles. On the particle side of things, we have this equation which relates the work function to the threshold frequency in the photoelectric effect. We've got this one which gives us the required stopping potential for photoelectrons. This gives us photon energies in terms of their frequency and wavelength. This momentum formula applies to both photons and particles. It gives us the wavelength of particles too. This gives us the energy of particles with zero rest mass, and this one tells us how much the wavelength of an X-ray photon increases after bouncing off an electron. Neither of these two are used in this unit, but they're used in Unit D. Here's a collection of mirrors and lenses we looked at in this unit. This is a convex or diverging mirror. Just picture the outside surface of a shiny sphere. This is a diverging lens. This is a concave or converging mirror. Now picture the inside surface of a shiny sphere. And lastly, this is a converging lens. When it comes to mirrors, both the object being viewed and the observer are on the same side, obviously. So with diverging mirrors, the principal focal point and the center of curvature are on the other side of the mirror. Their focal lengths are negative by convention. When it comes to lenses, the object being viewed is on one side and the observer is on the other. With diverging lenses, the optical center is in the center of the lens, go figure, and the virtual principal focus is on the object side of the lens. So their focal lengths, as with diverging mirrors, are negative by convention. For converging mirrors, the principal focal point and the center of curvature are on the same side as the object and observer. Their focal lengths are positive by convention. For converging lenses, the optical center is on the moon. No, it's in the center of the lens. The principal focal point is on the observer side this time, though. This is different than the diverging lens. Their focal lengths, as with converging mirrors, are positive by convention. When light travels from one medium to another, it changes its speed, sort of like what happens when you drive a car from the pavement to the sand or vice versa. If light strikes the interface at an angle, its direction also changes. In order to predict what will happen to the light when it switches media, we can use the expanded version of Snell's law, which relates the incident and refracted angles of light to the indices of refraction of the two media, the speed of light in the two media, and the wavelength of light in the two media. When light goes from a faster to a slower medium, it bends towards the normal. The result is the same if you drive your car from a faster medium, like pavement, to a slower medium, like sand. So we're driving along pavement in our car at a certain angle of incidence when we hit the sand. The green tire touches the sand first and loses traction. Meanwhile, the tires on the left continue to turn where there's still a lot of grippage. The car turns towards the normal until both front tires are on the sand, and the car continues along in a straight line through the sand. When light goes from a slower to a faster medium, it bends away from the normal. The result is the same if you drive your car from a slower to a faster medium. Now we're driving through the sand in our car at a certain angle of incidence when we hit the pavement. The green tire touches the pavement first and gains traction. This added traction on the front right tire turns the car away from the normal. After a while, both front tires reach the pavement, and the car continues along in a straight line. There exists a certain angle of incidence called the critical angle where the angle of refraction is 90 degrees. At this angle and beyond, we have total internal reflection. Using Snell's law with the angle of refraction at 90 degrees, we can find the critical angle for two media. Divide both sides of this equation by the initial index of refraction, and then take the inverse sign of both sides of this equation. Keep in mind this will only work if you're going from a slower to a faster medium. Your calculator will probably explode if you try otherwise. In this situation, we're driving through the sand in our car at the critical angle. As before, the green tire hits the pavement first, gains traction, and turns the car away from the normal, this time at 90 degrees. For this analogy to work, all the tires should probably be in the sand at this point, but hopefully you get the idea. Beyond the critical angle, photons will actually be reflected, almost as though they were interacting with a mirror. When we're working with an interference pattern and we have the ability to measure small angles, we have the option to use this relation, where d is the slit separation, theta is the angle between the central max and the nth antinode, and n is that nth antinode. I've made a note to remind you that this is the equation you'll find in your data booklet. This is for antinodes, or the bright bands. If you want the equivalent formula for nodes, or the dark bands, just replace n in the equation to the right with n minus 1/2. It may actually be a bit difficult to tell which antinode is the central one when you examine an interference pattern up close. Any one of these might be at the center. We can at least simplify our lives a bit by using this equation. Thankfully, no angle measurements required here, where x is the distance from the central antinode to the nth antinode, d is the slit or line separation, n is the nth antinode, and L is the distance to the screen. If we want to know the formula for the nodes or the dark bands, we just sub in n minus 1/2 for n. We had a brief look at blackbody radiation curves in this unit. You should at least know that a blackbody's energy is carried away in discrete packets called photons, and photons are somewhat picky with the amount of energy they'll carry away. Contrary to the classical picture, the bulk of the energy is usually not carried away by high-frequency photons. Otherwise, we'd be bombarded with high-frequency radiation anytime we lit a match. Click on the graph here to find out more about Max Planck and the origin of the quantum. The photoelectric effect is what happens when you shine a light of sufficient frequency on a metal surface. It's the one specific thing that was mentioned in Einstein's Nobel Prize in 1922. Seems a bit strange considering all the other insanely important contributions he made to the field. Anyways, we're going to look at the photoelectric effect in a different way here. I want you to think of a vending machine as the metal and all the candy inside it as its electrons. Let's see if we can get some candy out of this thing. Let's see if this radio jockey can help us out. He'll be our representative for radio waves. What happens when he hits the vending machine? Nothing. Alright, so let's dial up the intensity. Let's get more radio jockeys hitting this vending machine per second. What happens then? More of nothing. These radio jockeys don't have enough energy to get stuff done. Might be all that time they spend at their desks. So let's step it up a bit. Maybe Arnold can help us out. He'll be our representative for UV radiation. He's got a bit of a tan there, which is from UV radiation. That works, right? Anyways, Arnold steps up to the plate, takes a crack at this vending machine. Kit Kat flies out with a small amount of energy. Alright, so let's dial up the intensity. Let's get more Arnolds hitting this vending machine per second. What's going to happen then? We get a number of Kit Kats flying out with the exact same energy as when one Arnold hit the vending machine. Let's take it further still. The Hulk will be our representative for gamma radiation because that's what gave him his power. By the way, if you're hoping to get superpowers from exposure to gamma radiation or nuclear waste, you'll probably be disappointed with the results. Just ask Adam West. Anyway, the Hulk steps up, hits the vending machine. Kit Kat flies out with quite a lot of energy. So let's dial up the intensity. Let's get more hulks per second hitting the vending machine. What happens then? We get a bunch of Kit Kats coming out with the same amount of energy as what was happening with a single hulk hitting the vending machine. So as we dialed up the frequency, we got higher energy Kit Kats out of the vending machine. Increasing the intensity didn't change the energy of the Kit Kats, there were just more of them with that exact same energy. And until we met a certain threshold frequency, we weren't getting any Kit Kats out of the machine. They had to overcome the work function of the vending machine before they could hope to escape. Some vending machines are just built stronger than others and require more of a smack to get the candy out. Here's an important equation that is not exactly on your formula sheet, but it might come in handy. It tells you whatever photon energy is left after the work function is cleared goes right into the kinetic energy of the photoelectron. The equation for Compton scattering comes straight from 2D collision analysis. Rather than two billiard balls though, we have an X-ray photon and an electron. The X-ray photon essentially comes in, bounces off an electron, and continues going about its business with a new direction and a reduced energy. Some of its energy was given to the electron in the collision. We can find out a lot from this collision by measuring the scattering angle of the X-ray photon. Here's the equation for Compton scattering in your data booklet. Because the X-ray lost energy, its final wavelength after the collision is longer. Smaller energy, larger wavelength. In this example, we have a converging lens with a focal length of 8 centimeters inside a computer projector. An LCD panel is positioned inside the projector that serves as an object for the lens. So if the LCD panel is located 8.10 centimeters from the lens inside the projector, how far away should the screen be placed so that a clear image is produced? So we have the object distance is given to us. The image distance is what we want to find out. So we'll start with the lens equation and plug in what we know. So positive 8 is the focal length, 8.10 is the object distance, and we want to find the image distance. Subtract 1 over 8.10 from both sides, giving us 0.00154 on the left. We'll invert both sides of this equation, and that'll give us the image distance, which is 648 centimeters. So we'll shrink that away. So if the LCD panel is 1.75 centimeters high, how large is the image on the screen? So we're given here the object height is 1.75 centimeters, and the image height is what we want to find out. So we'll start with this equation on our formula sheet and plug in what we know. We have the object height, 1.75 centimeters. The image distance is 648 centimeters. The object distance is 8.10 centimeters. So we'll multiply 1.75 by both sides, giving us the image height of 140 centimeters. Next up, if the screen is moved 3 meters closer to the projector, how far must the object now be from the lens in order to generate a focused image? So the image distance is reduced from the original 648 by 300 centimeters. So the new image distance is 348 centimeters. The object distance is what we want to find out. So using the lens equation, we'll sub in what we know. 8 is the focal length, 348 is the image distance. Subtract 1 over 348 from both sides of this equation, giving us 0.122 roughly on the left, equals 1 over the object distance. We're going to invert both sides of this equation, giving us the object distance, which is 8.2 centimeters. In this example, we're asked to predict the image characteristics of a candle when viewed through a diverging lens. So don't forget the focal length is negative. We could jump straight into the math here, but we'll start with a rough diagram to get a sense of what sort of image we might expect. So we'll start by drawing a ray parallel to the principal axis. It looks like it's coming from the principal focus. The second ray shoots straight toward the secondary focus, but looks like it's coming from a line parallel to the principal axis. The third ray we draw goes straight through the optical center, and the image forms of the candle where the lines intersect. So we can see right away that we should expect a diminished virtual image from this diagram. If we need to find the exact image location relative to the lens, we got to do a bit of math. So start with the lens equation and plug in what we know. The focal length is negative because it's a diverging lens. Subtract 1 over 100 from both sides of that equation, and then we're going to invert that next equation, giving us the image distance of 20 centimeters. The negative sign tells us that the image is virtual. Next up, we're asked to find the image height. From the diagram, we can tell that the image of the candle is smaller, but by how much is what we want to find out. So we'll start with this equation from the formula sheet, and as always, plug in what we know. The height of the object is 10 centimeters, the image distance is -20, don't forget it's a double negative there. The object distance is 100, so isolate for the height of the image. The height of the image is 2 centimeters. We can get an answer to part C off the diagram pretty quick, but we can also get an answer considering the value and sign of part B and the sign of part A. Respectively, these tell us that the image is diminished, erect, and virtual. Next up, we've got a diffraction grating with 1,000 lines per centimeter. When red light of 750 nanometers is incident upon the grating, what is the separation between bright antinodes on a screen 3 meters away? So first we're going to try to figure out the distance between two consecutive lines. Start with 1,000 lines per centimeter, invert it, tells us it's 1 centimeter per 1,000 lines. Convert centimeters into meters, so we have the distance between neighboring lines is 1 times 10 to the minus 5 meters. We also know that the wavelength is 750 nanometers, and the distance to the screen is 3 meters. So we need to figure out the distance from the 0th central antinode to the first antinode. So that's that distance on the diagram. So we'll use this equation, xd over nl. Plug in what we know. We use 1 for n because it's the distance to the first antinode, 3 meters to the screen, and then we're going to isolate for x. So eventually we end up getting that x is 0.225 meters, or about 23 centimeters. In this question, we're looking for the kinetic energy of a photoelectron liberated from a piece of cesium by a 400 nanometer photon. That photon needs to be at least 2.10 electron volts for an electron to even consider leaving the cesium. Any energy in excess of 2.10 electron volts is put into the kinetic energy of the photoelectron. So here's the relation we need to find the answer to this question. Notice it's not explicitly in the data booklet. Very interesting. So let's continue. Put in Planck's constant in terms of electron volts. We'll need the wave equation, isolate it for the frequency. So that's the frequency of a 400 nanometer photon. We'll subtract the work function of the piece of cesium, and we'll figure out the first bit. So that's 3.105 electron volts there. Subtract the work function again. The excess energy is about 1 electron volt. So the kinetic energy of a photoelectron in this situation is 1.01 electron volts. Next up, what stopping voltage is needed to stop an electron with this kinetic energy? Well, it's pretty simple. It's 1.01 volts. Life gets a bit easier if we measure energies in electron volts when we're dealing with elementary charges. If you insist on doing this question in SI units, here's how you go about doing it. Switch the energy you found in part A to an amount in joules, plop in the elementary charge, and solve for the stopping voltage. So in this case, you're multiplying and dividing by the same number, 1.60 times 10 to the negative 19. So you end up with a stopping voltage of 1.01 joules per coulomb, or 1.01 volts.